I'm John Regehr. I'm a professor at the University of Utah, and I'm going to talk about something that I've worked on for the last 15 years or so. So I'm just sort of curious, how many people here have reported a compiler bug? Good. How many people, so this should be a superset, right? Have been 100% sure you've seen a compiler bug, but maybe didn't report one. Yeah, sure. Reporting one's a pain, right? It's sort of, it takes work. And how many people probably ran into one, but aren't 100% certain? Yeah, sometimes it's hard, right? Because like the compiler bugs are in the kind of corner cases of the standard where you don't understand and the compiler developers don't either, right? So like, sometimes we're not sure. If it crashes, that's easy. But today I'm going to talk more about the kind of bugs that are not so easy. So compiler bugs show themselves in a variety of ways, right? Sometimes the compiler just exits abnormally. Other times it, quite commonly actually, emits improper debug code for improper debug symbols and things. Sometimes it errors out when it shouldn't have. Sometimes it shouldn't error out, but it does. LLVM sort of likes to hang forever because sometimes two optimizations kind of get in a fight and just undo each other forever. And so the compiler hangs. And the kind of compiler bug that I sort of probably will focus on the most here is the kind where it emits code silently, without telling you that doesn't do what you said to do. That's kind of the most pernicious kind probably. And, a lot of these, anyway, those are the kind that I sort of have dealt with the most. So let me just tell sort of a really quick story about an embedded C compiler. So I was teaching an embedded software class back when I was a fresh, young, new professor, 20 years ago. And we spent a lot of time in the class just looking at code. We'd look at some C code and we look at the translation. And of course, this is what you do in an embedded systems class. You're so close to the metal, you want to sort of know what the compiler's doing, what it's thinking. And a student sort of said, hey, professor, that looks wrong. The translation looked wrong, and I hadn't noticed this. And the student was right. And I just assumed I had done a cut and paste error while making my slides, but I checked later that evening, and I hadn't made a cut and paste error. The compiler was wrong. And on Tuesday night, John Hayed sort of mentioned this kind of phenomenon where you sort of start to look into something, and each time you look into it, something gets worse, and you get angrier and more frustrated. And it just really started to bother me more and more over the succeeding years. This thing, which we trust to do the job, just wasn't doing the job. And this particular embedded compiler, I won't mention its name, but it was really wrong. It was almost harder to get it to generate correct code than incorrect code. Of course, that's not the case for most compilers we use. And I don't, unfortunately, have the example anymore of that compiler. I've lost, it's sort of the actual code snippets have been lost to time. But I'll show you a different example. So here's an embedded systems-ish snippet of code. You wouldn't write this code, right? This isn't useful, but so we have volatile in X, and we load it and then store it. And according to the rules for volatile, this needs to result at the generated code level as a load and a store of the same value. And MSP 430 GCC, at the time I started looking into all this, emitted just a return. It just said optimize it away. And actually still does. I just went to Compiler Explorer just before this talk, and the current version still does this. Like, what the hell? Like, how do embedded systems work if it's just optimizing away accesses to volatiles? I don't know. Right? So, some of these things don't have, here's another one where I don't have a good answer. So this is a function, so this is a silly function, right? This is a silly small function designed to expose a compiler bug, but this function has to return 0 on, common implementation-defined platforms. And years ago, the then current version of Ubuntu Linux shipped with a version of GCC that made it return 1 at all optimization levels. And like every single package, including the kernel on this distribution, was compiled with this compiler. Like, how did it work? Like, I don't know. I've never even understood this, right? Like, and this particular bug was, a very nasty one. It wasn't actually a GCC defect. It was that the Ubuntu people had somehow saw fit to apply about 5 megabytes of patches to GCC and then deploy that one. And they broke things sort of badly. So I don't want to give you the impression that all the compiler bugs are 20 years ago. So here's one that's just from last month. So here's a compiler, a GCC developer, replying to my student who reported the test case with a better reduced version of the test case. And here the crux of it is a comparison or the complement of the comparison. GCC got that wrong a month ago. And it had been sitting there for like a long time. Maybe you just don't do that, right? That's sort of stupid code. Maybe you just don't do that. But that was sitting in mainline GCC for years. There's sort of weird stuff going on where there can be some pretty significantly broken stuff sitting there, and we just don't know. And as a user, as a developer, because undefined behavior in these languages is so pernicious, we often just assume it's our fault, right? Or something's going wrong, you just tweak the code, you're like, what the hell? You start rewriting it different ways. You often work around compiler bugs without even noticing it. It's weird. It's a weird world we live in. So those were wrong code bugs, and I'll just show an example of a crash bug. So here's one from last summer. So this particular code snippet here made GCC seg fault, and why that particular snippet of code, the GCC developers knew, and so I'm including links at the bottom of a lot of these slides. So I like to show the receipts for these kind of things. So if you do feel like getting the slides later and clicking on these, you can read the whole discussion. But anyway, of course they fixed this kind of thing. So those are a few examples, and so those are some bad things, right? I showed you some bad things that we don't want the compiler to do. But what do we know about correct compilers? I mean, should we just say it's one that never does the bad things? That's not a very good definition, right? I mean, in practice, that's what we want, but it's not a constructive definition, right? It doesn't tell us what we should be building. It tells us what we shouldn't be building. And it's not so easy to say what a correct compiler is, and that leads us to problems if we decide to prove compilers correct. So compilers are like the most eminently provable math objects on the world because they're purely mathematical, right? They take a mathematical construct, a source language, they turn it into a different mathematical construct, a target language, and in the middle, they're not concurrent, they're not depending on very much. It's just a pure function, essentially, from an input to an output. We should be able to prove these correct, but to do that, we need to know what they should do. And to know what they should do, we need a semantics for the source language. And that doesn't even exist for common languages like, for example, Swift or C++. Creating a mechanized formal semantic for C++ is, nobody's ever even, I think, made a serious try at it. It's just too hard. And other languages are in the same boat. Rust has mechanized formal semantics, but none of them that I looked at I thought were probably complete. I could be wrong about that, but Swift definitely doesn't have one. And a mechanized formal semantics is just table stakes. That's just the very first thing you need. And once you have that, you can start to try to prove a compiler correct, but realistically, that's proving a proved correct compiler is not compatible with compiler development as we understand it in the world. It's too onerous. It imposes too big of a burden on compiler developers. They can't keep implementing optimizations. They can't keep implementing new language standards. It's just sort of, in my view, in the short and medium term, just a non-starter. We're not going to do this. It's not what we want. What we want is compilers that don't have a lot of bugs, but this isn't the way to get there, in my opinion. So where are compilers incorrect? Well, the specification can be hard to understand. So I've run into many cases where I found something where my reading of, for example, the C standard and the compiler developers just differed. And sometimes they were right, sometimes I was right? It's English, and it's not even really very good English often. There's legitimate ambiguity. Developers often haven't had time to catch up with the specification, especially in C++. Like, Visual C++ was, I think, slightly incompatible in its templates with the specification for years and years and years and years, right? They just couldn't quite get over that hurdle to, making templates work. Sometimes we just don't have enough test cases. There's all sorts of reasons why compilers are wrong. And the one that kind of most interests me sort of professionally is developers miss corner cases. And the reason that that's sort of the most interesting is these other ones are more sort of human software process issues often, hard to attack as an academic. Logic errors I can attack. So let me show you a logic error. This is a corner case that I really enjoyed finding. This is maybe last spring or something. So LLVM internally has these intrinsic functions for checked arithmetic operations. So one of them is signed multiply by overflow. It takes two inputs, it multiplies them, and it returns a pair. The pair contains the result, the 2's complement result, at the same bit width as the inputs. And so here I should say that these particular intrinsics work at any width. You can pass them any width integer, and they just do what they should do. So it returns the result at the bit width, and then the overflow is a Boolean flag indicating whether overflow occurred. So that's straightforward enough. And of course, the reason we do this is to expose, provide sort of a uniform access to the processor's condition code flags, which are typically not accessible from the source level. So this is inside LLVM where we need efficient access to these lower level abstractions. So the LLVM middle end, which is where a lot of the optimizations happen, and also in its back ends, there's some redundancy in optimizations. They all contained an optimization which took a sign multiply with overflow of a and 1, so any arbitrary integer and 1, and reduce that to a pair, a and false. So if you multiply a times 1, you get a back, and it doesn't overflow, right? Does that seem fairly clear? Can we buy it? It's wrong. It took me a while to see this. The theorem prover I was interacting with told me, found a bug related to this, and I thought the theorem prover was wrong for like an hour before I figured it out. Does anybody, it's a nasty corner case. It's a 1-bit multiply, sign multiply with overflow. Do you see the problem now? What does 1 mean? 2's complement y's at 1 bit wide. It's not 1, right? It's -1. There's no identity element for multiplication at 1 bit wide. The optimization breaks. Does anybody care? I don't know. I just enjoyed finding it because I thought it was very funny. And of course, they have to fix this kind of thing, because even if it's funny and even if nobody cares, it's still mathematically wrong. And as engineers, we fix that stuff. So anyway, I show this to illustrate how hard these corner cases can be to see. I don't think that many people in this room, and certainly not me, would have seen this problem just kind of while we were coding it up, right? That's a pretty innocuous looking optimization, and it's not right. And so that's we see a lot of stuff like this. So now it comes time to sort of ask you a question. Do you want your compiler to be correct? Raise your hand if you want your compiler to be correct. Yeah, but that's like security, right? We all want security, but we don't. We truly don't want security because we want a usable phone. The secure phone is the one that's buried in concrete and dropped into the ocean, right? That's a secure phone. We want to use it. We want insecure phones. We don't want correct compilers. We want sort of correct compilers. So if you had to rewrite all of your code, if I gave you a correct compiler in a language that's different than your code base, I don't think you'd care, right? If I gave you a correct compiler for which the license cost as much as your salary, I don't think you'd switch to it. You wouldn't switch to it if it didn't optimize. You wouldn't switch to it if it didn't support templates or something, right? We want correctness, but we don't want it that badly. There's an optimum point for correctness, and it's not all the way at the correct side, right? It's just sort of a reality of sort of engineering and economic life. And so engineering, there's a lot of definitions for engineering, but one that I like is, it's accomplishing goals with limited resources. If resources are unlimited, it's not engineering, it's imagination or playing or something, right? This isn't something that's interesting or exists. So given that compiler engineers only have, they're expensive people, there's not that many of them, and every day they have to do something, right? They have to wake up, go to their computer and do something. What are they going to do? Are they going to fix bugs in correctness reported by users? Are they going to try to find new correctness bugs? Are they going to re-engineer parts of the compiler that have been incredibly troublesome and prone to bugs so they are less prone to bugs? What are they going to do? Well, it turns out they're probably not going to do any of this, right? They're not going to do any of this. What are they going to do? They're going to do what they're paid to do, right? Everybody makes a salary. They're going to probably make the optimizer better. They're going to probably support C23. They're probably going to target the new random variant of RISC-V that came out this month before a new variant comes out, right? That's what they're going to do. They're going to do their day job. People also fix bugs, but again, the optimum point for correctness and bug fixing isn't at completely correct. That's not really achievable in any sort of time frame. And there's a really nice paper that I found a while ago, and not that many people know it, and I really, really love this paper. It's called The Impact of Economics on Compiler Optimization. So here, the guy, Robison, the author, looked at all 47,000 papers on economics, electronically, obviously, and all 12,000 papers on compiler optimization, and he found one that had a meaningful discussion of the impact of economics on compiler optimization. So then he goes and writes a short paper on this, and it's totally worth reading. It's a really sort of nice short paper. Nobody so far has written the impact of economics on compiler correctness, so, oh well, I'll just be waiting. So, as I've been saying, there's a bit of a global optimum here where if we look at compiler quality as a function of, we could spend all of our development effort fixing bugs, in which case we'd never add features. That compiler sucks, right? Nobody wants it. We can also spend all of our effort on new features and never fix a bug. Nobody wants that one either. It's just going to crash every single time you use it. There's an optimum point in the middle. But here's the deal. This optimal point is a function of these underlying technologies, right? We can shift these curves by shifting how the underlying technologies work, and that's been sort of my goal since about 2010. Trying to do research projects that shift the economics, maybe just a little bit, right? But that shift the economics so that maybe we could reach an optimal point that's a little bit better than the natural one, which we sort of naturally get if people just do what they want. So what does that mean in practice? That means stuff like, well, maybe we can make it a lot easier to find compiler bugs. Maybe we could make it a lot easier to isolate the root cause of a compiler bug. Maybe we can help compiler users disambiguate when the problem is not the compiler. People used to blame the compiler a lot for undefined behavior problems. The GMP, does anybody use the GNU multi-precision library, GMP? It's a big nom library. It had something right on the web page that said, GCC frequently miscompiles our library. But when I went looking for undefined behaviors in the GMP library, it had a lot of them, all right? I think they were probably wrong. I mean, maybe not 100% wrong, but they were wrong a lot of the time. They just had bugs that they didn't understand. In recent years, as our understanding of undefined behavior has gotten better and better, we've seen a lot less blaming the compiler when the compiler isn't wrong. Because as I've been showing you, the compiler is wrong often enough, we don't need to blame it when it isn't wrong. So what else can we do? We can prove that the compiler did the right thing, and then we could generate parts of the compiler automatically. And I mentioned these specific list of things because these are all things that I've done, all research projects that I've done. And I'm going to tell you about, I don't have time to tell you about all of them, but I can tell you about a couple of them. So first I'm going to tell you about how my research group found and reported more than 1,000 compiler bugs. So when I started trying to think about, so I already sort of set the stage for you a little bit where I told you that I had sort of eventually noticed that compiler bugs were a lot more common than I had thought. And I started to find them more and more and more. But finding them by hand is incredibly dissatisfying, right? You can only do so in so much of this. And then I remembered that years and years ago, I had seen this really cool paper, and it stuck in my mind very forcefully because Jim Gray had mentioned it to me, and he had been extremely excited about this paper, and he was a very contagious sort of excitement kind of man, and I got excited about it. And this was massive stochastic testing of SQL, which basically just means fuzzing a database, right? Making random SQL queries, submitting them to multiple databases, and they were finding things like SQL Server like exponentiated wrong or something. Like it couldn't compute an exponent. Like, what the hell? So this is a really cool paper that kind of popped into my head. And then there was another one that sort of happened to be from the same year, Differential Testing for Software by McKeeman. And this one was a C compiler fuzzer that McKeeman had written back in 1998 or prior to 1998. And this is a really cool paper. It just really stuck in my mind as, he had just had these amazing findings. So I these techniques had been sitting there, so we went and basically adopted them. So we wrote a program called CSmith that my group wrote, and it generates random C code. And I wasn't the main author of CSmith, one of my students was, but I was the main one who reported the bugs. And over the years, I reported, with my, just by myself, 500 and some. And you sort of learn a lot while you're doing this. And one of my very favorite moments of my professional life was when CSmith got a Christmas card from an industrial compiler development team. They had all signed it, and they just had really enjoyed using CSmith. It had just found a ton of, they didn't tell me how many, right? But this is an open source tool. They had clearly found it worthwhile enough to actually send me a Christmas card addressed to CSmith. I was super happy. It made me very happy for this to happen. But anyway, CSmith is old news. We're not working on it anymore. I don't really want to talk about it. What I'd like to talk about is its successor, which I have a soon-to-graduate student who wrote a CSmith successor. I'll tell you a little bit about that. It's like CSmith, but it's better. And what I want to start talking about is the key to making one of these tools work well is it needs to be expressive, and it needs to have certain properties that let you find wrong code bugs. So expressiveness just means generating a lot of different kinds of code, and having a single interpretation means that if you run the program, it has to do a certain thing. And of course, that's important because a program that has undefined behaviors doesn't have to do a certain thing. It can do like anything. So if you run the program generated by the compiler and it does something random, you can make no inferences, right? On the other hand, if you run a program with a single interpretation and it does something random like crashes, now you can make a strong inference that the compiler has a bug. So we need both of these properties, and let's talk about that a little more. So if we only care about expressiveness, generating random code is easy. You just generate any kind of crap you want. And if dereferencing a pointer goes off into space somewhere, just do it, all right? This doesn't give us what we want. It's easy, it's not useful. Similarly, if we only care about the single interpretation thing, we can generate a lot of random code. So maybe I restrict myself to programs that look like the one below, right? That's not gonna find compiler bugs, even though I can generate an infinite number of programs that have that form, that have that general syntactic form, all right? So we need to do both of these things, and doing them both is really hard. And it took us a long time. Each of these C compiler fuzzers cost one of my students, 4 or 5 years of their lives, right? This is a fairly significant engineering effort. On the other hand, 5 person years isn't very big industrially, but academically it's big. It's sort of at the limit of what I can do in academia. Give me a 50-person industrial team, and I can do different things, but at a university, this is about the most I can do. So let's talk about this single interpretation constraint. So a C and C++ program that we generate needs to be free of undefined behaviors and not rely on unspecified behaviors. And in some ideal world, maybe it wouldn't rely on implementation-defined behaviors either, but in practice, we just don't bother. No C program really fails to rely on implementation-defined behaviors, and so we don't bother with this either. But we do have to avoid the first two things. And so what I want to show you is a technique that we used in this second compiler fuzzer, YARPGen, that was different than what we did in CSmith for avoiding undefined behavior. So we're generating arithmetic expressions that are going to be part of a random program. And here's a tiny fragment of an arithmetic expression that's going to be in a random program. We generate an add operator, and then we're going to add int max and 42. Or we're going to add a and b, which at that program point happen to have the values int max and 42. So that's bad, right? We don't want that to happen. That's undefined. The program could explode. The computer could melt, whatever. We don't want to do it. So what we do is we just do something really simple. We have a little canned rewrite that we use that transforms the addition to a subtraction, and now it becomes defined. That was easy. We can stack this sort of concept, and we apply these kind of rewrites bottom up to a randomly generated expression. And when we get to the root, we have a full expression that's defined. And this all assumes that we know the values flowing into it. And I'm not going to talk about how we ensure that, but we ensure that we know the values flowing into it. But crucially, the compiler can't know the values flowing into it, if this makes sense. The compiler has to be solving a general problem. We only reason about a specific problem. And this gives us an incredibly sort of one-sided weapon against the compiler that lets us really break compilers fairly easily. So we can generate these arithmetic expression trees, and here I'll show you sort of the full table of little rewrite rules that let us generate arithmetic expressions avoiding undefined behavior. It's just a lot of little tweaks to things. But again, if you take a big random expression and apply these bottom up, you get something that actually works. And then you put a bunch of those together into a function, and you put a bunch of those functions into a program, and now you have a program that has the desired property. That's only for arithmetic expressions. There's a completely separate set of rules and rewrites and things that work for pointers and arrays and things, and I'm just not going to bother talking about that. So that sort of solve that problem, but you've noticed that we've relied on knowing the values flowing through our program, and that makes extending this scheme to loop programs hard, because we don't want to analyze all loop iterations. So what we do is we sort of do some tricks. We have some various tricks where the actual loop behavior is fairly restricted. Like, for example, it might only execute once, but the compiler doesn't know this, so it's solving a general case. It might execute with the same values flowing through it on every loop iteration. So that's two different schemes now. And again, we hide these things from the compiler. We hide these things, so the compiler has to solve a general problem. We're solving a specific problem, and that's why we, with a fairly lightweight engineering, can generate pretty tough things to compile. So anyway, we hide all of these tricks from the compiler, and this allows us to do some pretty good compiler fuzzing. And the reason we started targeting loops is because compiler loop optimizers have gotten pretty sophisticated in recent years, driven by big data, machine learning, AI. All these things have made lots of loops, right? Compiler loop optimizers like Poly, for example. There's never been a version of Poly that we couldn't just break in like 10 seconds. I mean, we want to break these loop optimizations. Has anybody looked at the scalar revolution module in LLVM? It sort of tries to predict which way a loop is going and what it's doing and how big the steps are. It is the most heinous mess I've ever seen in my life. I've never had any sense that I had any clue what it was really doing. We want to fuzz the hell out of that kind of thing, because if I can't figure it out, probably the other people can't either, right? They're not that much smarter than me. Do the tricks, okay, so Andre's question is, do the tricks we play reduce the bugs we can find? Sometimes, and we don't know, are the answers. Yeah, these questions are very hard to answer, but probably. Sometimes for sure. Other times, we suspect maybe. It's just hard to know. But the tricks are all we have. So, and they get us pretty far. So, but that's a very good question, yeah. But so what I want to talk about now is, so I've talked about generating code that has the desired properties that you need to fuzz a compiler and find wrong code bugs. And so I'll tell you now about making expressive loops. And this is particularly interesting and fun because compiler loop optimizers look for extremely specific idioms, extremely specific loop idioms. And I'll show you one. So compilers like to do loop fusion. you can only do loop fusion when the two loops are next to each other, they have the same iteration space, and they lack certain kinds of dependencies that would break loop fusion. Dependencies that would make, running the two loops in the same loop return a different result. So the compiler does some conservative checks, and it turns out that if you generate purely random loopy code, you almost never, and we checked this, right? We basically never trigger loop fusion. So we basically we have a sort of a higher level intermediate representation for the partially generated random program that includes special commands for generating fusible loops. Okay, so that's one thing we did. Another thing we did is we want to trigger stencil optimizations. So stencil codes are ones that look at a sort of a window. Here I'm showing an example that looks at a one-dimensional window of code, 3 pixels in a row. But it could be, more commonly it'd be a square of pixels in an image that we're doing some sort of a stencil computation of. So a stencil computation looks at this window, a small window of an array, and computes a new value out of it to store into a destination array. So LLVM and GCC are extremely clever with stencil codes because they're common and they're performance critical. So here you can see on the right some ARM object code where at the left we've loaded 3 array values. Does that kind of make sense? We've loaded 3 different array values per loop iteration. But the object code at the right loads one array value per loop iteration. That's really sort of magical. And so what it does is it loads the farthest one up, the I+1, and it forwards that to subsequent loop iterations using registers. So if you look at the code carefully, I won't try to explain it, and it'll even do this for 6 values or 7, until eventually it runs out of registers and stops doing this. But it's very clever, and you can reduce the memory traffic by quite a lot for these extremely performance critical codes. So we need to trigger that kind of optimization because that's the kind of thing where the compiler writers are being incredibly clever. That's where they're going to go wrong. We need to trigger it. We can't find bugs in it if we can't trigger the optimizations. So again, we need some canned support for stencils. Okay, so I've showed you 2 kinds of canned support for loop-ish idioms, and we ended up with 10 of those, sort of very general purpose, kinds of code structures that loop optimizers look for. And the real trick here is that these are sort of parameterized structure. They're structure that's parameterized by randomness, and they compose with each other. So for example, we can have a reduction of dimension and compose that with a stencil computation, and you get something like what we show on the slide here. And these combined with fusible loops, these things compose fairly nicely. We get pretty dense collections of pretty interesting loop idioms that look sort of like what people would have written while retaining enough randomness to really make the compiler have to work hard to do a correct job. So that's what YARPGen did. So the first generation of YARPGen sort of didn't focus on loops, didn't do very interesting stuff with loops. The second version of it, my student focused heavily on loops, and this is really fun. And so in total, across the 2 versions, we got 183 wrong code bugs, mostly in GCC and LLVM, but also in some other compilers, 157 crash bugs, and then the nice thing is most of these have been fixed. So if the compiler developers weren't fixing the bugs we submitted, this would be the most useless effort on the planet. Does that kind of make sense? This benefits nobody if we just add issues that people don't want to fix. But the thing is, compiler developers, despite the fact that, as I said earlier, they had something else to do that day, they always have something else to do that day. Despite that fact, they do fix these bugs. And a lot of it is because open source developers aren't as beholden to corporations as other people are. They often have, I'm not sure about this, but it seems like the open source world, with public issue trackers, people are more likely to fix bugs. The bugs that, when we first started doing CSmith, I started submitting bugs to ARM's compiler team, to Suns, which existed at the time. None of them cared. They reacted somewhere between disdain and hostility, because I wasn't a customer, right? I wasn't paying. Their job was to work for the customer. They didn't have, for whatever reason, a lot of professional pride in their project. They just wanted to work on the bottom line. The open source developers fixed them, and it's really good. So that's how we can sort of move forward. And what really happened, I think, is these compilers kind of, their complexity exceeded what people could really understand. They got really big and bloated, really smart, and there were just a lot of latent bugs. So when CSmith laid into these compilers, it was just like farming, right? It was just like farming bugs. I mean, it took a while to even generate programs that they wouldn't miscompile. It was weird. And eventually, over the years, the compilers become resistant to our tools. And eventually, currently, if you use YARPGen on the latest trunk version of GCC or LLVM, it might take a couple of days to find a bug. And so that's what we want, right? That's what we want is reach a state where we've sort of saturated the ability of our tool to find bugs, and then we can sort of keep running it. And now we're finding new bugs instead of old bugs. And new bugs are awesome. Old bugs suck because the person's probably not working at the company anymore. And if they are, they're doing something different. The bug that just got committed yesterday, the code is fresh in somebody's mind. If I can report that, within a couple of days of it getting committed to the code base, they remember what they're doing, they're still working on it, they probably have time, they're gonna fix it. And so it took a long time, but we eventually, with these compilers, got more or less to where we wanted to be. Okay, so YARPGen's primary author, actually essentially only author, is my PhD student Sevalid. And YARPGen, he put a lot of effort into writing a good driver for it. Like it'll run creduce when it finds something. It'll minimize the bug that it found. It'll use all the cores on your machine. It's really easy to use YARPGen. It's open source. So if you feel like trying to break a compiler, it's out there waiting for you. But if you do use it, we'd love to know, because a lot of people use it and never tell us. And one thing we did is we got the GCC people to keep a meta bug for YARPGen, where if a bug is found using YARPGen, they add it to a list tracking the bugs found with YARPGen. And this is really cool because it helps us keep score. There used to be a compiler fuzzer for JavaScript called JS FunFuzz, and Mozilla eventually closed off access to that page, to the meta bug for it, but it had well over 1,000 bugs. It was just this massive wall. SpiderMonkey was just an unbelievable pile of bugs when JS FunFuzz sort of laid into it and just completely found so many. It was unbelievable just looking at what the author of JS FunFuzz accomplished. And of course, JavaScript is security critical, so that really mattered there. Okay, so I'm going to switch gears a little bit now. So let's talk about something that it's a little bit more current work. So like I say, YARPGen is, my student's graduating soon. He's kind of wrapping up his main development on it, unless he happens to get hired by a company who wants to pay him to work on it. And, that'd be nice, but I'm not sure if that'll happen. So let's talk about generating parts of a compiler automatically. And so why would you want to generate parts of a compiler automatically? It's because they're buggy when you write them by hand. That's why I want to do it. I mean, there's lots of other reasons, but from the compiler bug point of view, if we can generate something systematically and automatically, we should do it. So let's talk about generating a people optimizer. So people optimizers are super fun artifacts. And something that's really interesting about people optimizers is that almost every compiler has one. It's usually the first optimizer that a compiler gets. So even really, really dumb basic compilers like written in Python for some little DSL, they get a people optimizer pretty quickly because they can clean up a lot of local inefficiencies in code, and they're simple, and you can sort of incrementally improve them. So what does a people optimization look like? Well, the one I've shown in the middle of the slide here is using a De Morgan law to do some arithmetic simplification. So the complement of A ANDed with the complement of B can be turned into the complement of A or B, saving one operation, right? It's 3 operations on the left-hand side, 2 operations on the right-hand side. That's more efficient. And so what a people optimizer is it's a collection of about 10,000 of these. In the case of LLVM, it's an absolutely gigantic number of these. And it turned out to be a truly big minefield of corner case errors because every single one of these, I'm making up 10,000, it's some number, but they're mixed together, so it's really hard to count them. So I don't know how many there are. But every single one of them is a separate opportunity to be wrong, and many of them involve very finicky reasoning. De Morgan here we're not going to get this wrong, right? But a lot of other ones are very tricky. And it turned out that when we started fuzzing LLVM using CSmith, the people optimizer was actually the single buggiest component of it. So I considered it really ripe for replacement. That's been on my list for a long time, and we finally, in the last recent years, got around to doing this project. So let's talk about how this works. So the first thing we did was something that turned out to not be necessarily the right solution, but I'm going to describe it kind of quickly anyway. We created a tool called a super optimizer. A super optimizer is an optimizer that uses meaningful search. So most compiler optimizations have no search component, right? They just decide whether to do something, and they just either do something or don't do something. Does that kind of make sense? They're not trying things and backing out and looking at the results and evaluating. They don't do that. They don't have time. Everybody hates a slow compiler, and search is not something we have time for in a compiler because it's getting this mountain of like 35 megabytes of C++ once you've expanded the includes, and there's no search. It's hard to even just get through it at all. Okay, So what the super optimizer does is slices out part of an LLVM function. So this is inside the compiler. So we have we're operating at the level of LLVM's intermediate representation here. It slices out part of the function, and it uses a technique called program synthesis to try to compute it, whatever that slice computed, it tries to do it more efficiently. And it uses program synthesis to do that. Program synthesis is sort of a slightly magical solver-based technique for creating code that conforms to a specification. So here the specification is the original sliced code, and we're just trying to synthesize something, and either synthesis succeeds, in which case we computed the value more efficiently, or it fails, in which case we just move on and we don't have a people optimization there. And in the super tool, after it computes a people optimization, can optionally apply it, actually do the optimization and optionally cache it for the future because synthesis is really slow. So this works. And so we're done? No, we're not done. We're not done at all. We're not even like a little bit done. So super is incredibly slow because it relies on making a massive number of calls to a theorem prover Z3 in order to do synthesis. So synthesis is this thing, it's based on a formal specification for LLVM intermediate representation. And, to evaluate the meaning of a piece of LLVM intermediate representation, we are asking Z3 lots of questions. And to do synthesis, we have to ask it a huge number of questions. So the search space is really very large. Super is incredibly slow. Nobody wants to load an optimization pass that makes their compiler 150 times slower. And 150 times is just a magic number. You can make super as fast or as slow as you want by tuning its synthesis. If you make it really fast, it doesn't do anything. And if you make it take 3 weeks, it'll do something, but nobody felt like waiting 3 weeks for their program to compile. Okay, so nobody wants a slow compiler, right? So the question is, what do we do next? So this is a way to get people optimizations for free at some level. We can automatically construct most of what we find in LLVM's people optimizers, or maybe not most of it, much of it. But it's impractical. So what are we going to do? So this is what my current student is working on. So let's talk about how super has impacted LLVM. It's impacted LLVM indirectly with a human in the loop. So what people do occasionally is they'll run super on some LLVM intermediate representation. It'll spit out some optimizations. Then they go ahead and look at those really carefully and implement them as part of the people optimizer, which is called inst-combine in LLVM. So that's how super has had impact on LLVM. And there's a bunch of LLVM optimizations that came from super, right? It's had a good amount of impact, but this isn't how we wanted to do it. We don't want the person doing this because it turns out that this process of manually taking something generated by super, which is a completely specific optimization, and generalizing it to make it something that can be used in a more general case inside the compiler, that's the hard part. That's the error-prone part. That's where people make mistakes, and it turned out we automated the wrong thing, basically. So spotting the missed optimization is what super's great at. That's not really the hardest part. The hard part is the next part. So now we next tried to attack the hard part. Let's talk about the hard part. So let's say super sees x times 2. It would synthesize x shift left by 1. On many platforms, that's considered desirable, right? The multiplier is a more expensive piece of hardware than a shifter. So that's a good optimization. That is not general, that's specific. The thing the compiler developer would implement is the generalized version of it. And how do we generalize this? Well, let's go through what our generalization toolchain does, and also this is basically mirrors what a compiler developer would do by hand, but again, they screw it up. This generalization part is hard. It's really not easy. Okay, so we have x times 2 being rewritten as x left shifted by 1. What do we need to do? What's the obvious thing to generalize first here? Who wants to just yell out? Yeah, 2 is a very weird choice of number. We don't want to just optimize multiplying by 2, right? That's stupid. Okay, so what do we want to do? Well, we want to multiply x times a constant, and then it's going to turn into shifting left by some other constant. Now, there's 2 problems with this. One is that we can't do that for all choices of C, right? This only works for specific choices of C. Somebody just yell it out. Powers of 2, of course. The other thing is we don't know how to compute D yet. Okay? So we've broken the optimization completely. So what do? Well, we're going to compute a precondition in order to make this optimization only fire when it's able to work. And so we do it like this. We add a precondition called, using a LLVM built-in primitive is power of 2. And if it is a power of 2, then we can fire the optimization. And how do we get the precondition? Well, we use program synthesis again. This has been the really fun part of this project is we had this program synthesis engine that we wrote for super. We just keep calling it again and again in different parts of this tool. And I'm not even going to tell you about all of them. I'm just going to tell you about a few of them. Okay. So this works, but we still haven't figured out how to compute D. And so now I've already told you how to compute D. What do? How do we figure out how to compute D? No, that's how you compute it, but how does my generalization tool do it? Program synthesis, right? Program synthesis. So we synthesize a log function of C, and now we get a complete optimization. This actually works. So this is a correct optimization. It's significantly more general. It hasn't been generalized completely yet, and so in one tiny way in which we can make it more general is we'd also like to apply this to the commuted version. That's pretty trivial. There's a very big missing part here, which is we want to make the thing work at different bit widths, and this turned out to be a pretty tricky problem. So in LLVM intermediate, inside the compiler, things can be arbitrary bit width, right? They're fixed width, but they're arbitrary. And when you build the LLVM compiler using itself, you see integers of every bit width from 1 to like 87. And then from 87, it's sparsely populated up to 320. Why do you see a 320-bit integer? I don't even remember. I looked into this one time. Why do we see every single integer width up to 87? It just does that. That's how it works. So optimizations need to work on values of arbitrary bit width. Okay, so I'm going to talk about that on the next slide, so I'm not going to talk about it too much here because it's hard. And I want to add that at every step of the generalization pipeline here, we're proving the thing correct. So we make sure to never break it, or I mean, we do break it sort of temporarily at step 2, right? But we make sure to move it back to a correct optimization using a tool called Alive2, which is something that my research group works on, although we're not the primary developers of it. It is a mechanized semantics for the LLVM intermediate representation that can basically tell you whether rewriting X to Y is legal according to the rules of LLVM optimizations. Yeah, I'm possibly simplifying here. I think this one works both ways. I think this one works both ways, but division certainly wouldn't, right? Unsigned and signed division are totally different. I'm pretty sure this one is okay for a bit vector X, right? It doesn't. We don't care if it's signed or unsigned. I'm pretty sure this works for the multiplication rules, but I'd have to go check. And so Alive2 is this tool we created. And so one thing that I did that I'm pretty happy with is you can hardly see it at the bottom there, but I made a compiler explorer instance that gives you access to Alive2. So you can paste something like this. So the question Andre asked is, does this work for in general? You could ask LLVM this question. I mean, you could ask Alive2 this question in a compiler explorer instance, and it would just do it. It would just tell you that it works. I hope. Anyway, so I didn't paste this exact stuff into Alive2. Anyway, so by creating this thing which can find compiler bugs, we also enabled the synthesis engine and this generalization engine to work, and so this has been really cool. Okay, so now I want to talk about the hard part here, which is the bit width independence. This turned out to be really difficult because, so you remember on the previous slide, we had to compute that constant D at any bit width. So we have to synthesize code which computes a specific constant that's in a bit width independent fashion. Does that kind of make sense? So it has to work at all bit widths. Humans do that naturally pretty well. It turned out to be really hard to get our synthesis engine to respect that constraint. And this is made more tricky by the fact that some optimizations aren't bit width independent. And I already showed you an example. That example, optimizing the sign multiply with overflow, worked at all bit width other than 1. There's plenty of optimizations that have weird, quirky corner cases at different bit widths, and we have to respect those in this pipeline, or else we'll get it wrong. And then finally, there's lots of optimizations, and I'm not going to show you any today, but there's lots of optimizations that involve values of different widths. We're truncating, we're extending, we're doing all sorts of crazy stuff. And working with those in a bit width independent fashion is actually quite difficult because, the shape of the thing you're dealing with, it's only sort of loosely constrained, right? It's not like the whole thing's at the same bit width. There's all sorts of variables going on. And, this is fairly hard stuff. So, furthermore, Z3, our underlying theorem prover, gives us essentially no help. Z3 can only answer questions about a specific bit width. And the general questions that we want to ask it, we can't ask it. We have to solve them separately ourselves. And there's a little bit of work on this in other theorem provers that aren't Z3, but it's not production ready. So we had to do this all ourselves. So we didn't understand how hard this would be or that this was really a real problem. And when my student and I finally figured out this was a problem, it set us back a year or so while we figured it all out. But on the plus side, we've sort of got a handle on this now, and it's really cool stuff. It's really cool work that I'm super excited about. Okay, so let's say that all works, and it mostly does, right? I'm telling you about a research project that's in a fairly good state at this point. So let's see what we do with it. So we take the generalized optimization, we turn it into C++. So C++ is LLVM's implementation language. So if we want to actually run our generalized optimizations, we have to turn them into C++. So we do it, and we get something, a little more complicated than what I'm showing you here, but it's basically the same thing. So let's just talk through this quickly. So there's a sort of a domain-specific pattern matcher in LLVM that this match construct gets us into. And so what we're saying is, for an instruction I, we want to match it if it's a multiplication of some value that's going to be stored into X and some constant that's going to be stored into C. So now if that matches, we're going to get an X and C, a specific X and C to work with. So that's nice. If it doesn't match, then we don't get these values, of course, and we just fall out. The MC mul means we're matching a commutative mul. It'll match X times C or C times X. That's sort of nice little freebie there. So if the match matches, so if the structural prerequisite for the optimization holds, and also the constant is a power of 2, then we can replace all uses of I with a fresh shift that we've created, a fresh left shift by the proper amount. So we generate this entirely automatically. This is not far from what a person would write. There's other cases where we generate really weird stuff because this synthesis engine is not constrained by how you think or how I think. It just creates random stuff. Some of this stuff is really hard to understand. Other times like this, it generates what we had sort of expected to see. And now we have an optimization code that we can load into an LLVM pass and just drop it into LLVM as a shared library and go. So we can turn off instacombine and we can turn on our thing and we can just go and it works. And it's very cool. It's not as good because we still have some things missing. Instacombine can play a lot of tricks that we can't play yet. Like for example, it has an alias analysis built in and we don't. But we're doing pretty well. So let me show you one more example here. When we look in the LLVM issue tracker, they track a lot of issues where there's a missing people optimization that they want that nobody's had time to implement yet. So here's one. So Nikita here has said on June 23rd said, well, here, so the thing at the top block of code, that's what Nikita noticed in some code that could be rewritten as the code below. And Nikita has very conveniently included a link to our compiler explorer instance to demonstrate that Nikita has found an optimization that's actually correct. So he just shells out to a compiler explorer, which proves it correct right on the fly for you right there. So this is correct. Nobody's had time to implement it yet. And the thing is, we can hand this particular thing to our generalization engine, and it just works. So we looked at maybe the last 10 of these, the most recent 10 of these in the LLVM issue tracker. It doesn't work for all of them, but it works for like 8 of them. And so this is, I think it stands to be something that might be able to change. Again, the premise here is that we wanted to change the economics of compiler development. If we can take a chunk of the compiler that people had a hard time getting right and just take it away from them, just give them correct code, maybe this changes the economics in a favorable fashion. I don't know. Maybe it frees up that engineer to fix a bug now instead of working on a people optimizer. Maybe it, maybe it has some other good effect. I don't know. We'll see. Okay. So I'm finishing up here. So generalizing optimization, so this is the PhD work for my student Manasij. We don't have a public version of this yet, but I really would like to put up a compiler explorer instance that not only has a live 2 in it like we've already done, but also has this generalization engine in it. So people can take stuff like Nikita's little issue, paste it in, and it just gives you the C++ code that would be suitable for pasting into the compiler. I really want to do that, but the thing is slow, it crashes, it's research software, Anyway, so in the future, I think that other parts of compilers are very amenable to this approach. Compilers, again, they're inherently mathematical objects. They're solving well-understood mathematical problems with well-understood properties. Everything they do is mechanizable, and yet they're these monster collections of C++. It's almost a travesty to see. It's just kind of wrong how we build them. And so, I think we can do better. And so, hopefully we can automatically construct lots of other parts too. I'm done, and thank you very much. Do we take a few minutes for questions, or should we just let everybody get to the train station? Okay. Okay, sure. that I didn't talk about, but that makes a very small test case typically for a bug trigger. And now you just look at it, look at all the, now you have to look at all the other bugs and try not to report it. We've deduplicated before. These are ones that the compiler developers have confirmed as real. Yeah, thank you. Yeah. Jason. Yeah, so the question is, Jason asks, have we learned novel optimizations? So far, it hasn't. The synthesis engine is not smart enough that it's reached what I would consider the point of sort of creativity. It's not at the algorithm level. It's not synthesizing like a, so has everybody looked at a fast pop count? Fast pop counts are awesome. I totally encourage you, if you haven't gone to look at the Wikipedia page for pop count, go look at the Wikipedia page for pop count or Hamming weight. It's a number of set bits in a word. The fastest algorithms for this are awesome. This technique in principle could make a faster one than anybody's ever seen if it exists. In practice, that's beyond the scope of our synthesis engine, which only makes a couple of instructions at a time. The search space is exponential. It's not to the point where it's making algorithms. It's still doing fairly basic things. I haven't seen any new discoveries yet, although it does come up with a lot of stuff that I don't understand. Yeah. There's a lot of them that I just don't understand, and you say, I believe the theorem prover, but I have no idea what the hell's going on. Victor.
In terms of synthesizing these people optimizations, is there any way to automate the process of reordering these optimizations and if combined?
Yeah.
Some of them are dependent on the order.
Okay, so Victor asked about optimization phase ordering. This is a hard problem. We don't have really very good solutions to that yet. There's actually a whole bunch of subtleties like that I didn't mention here that we're sort of working on. We don't necessarily have great ideas. What I'll just say is these mechanically discovered optimizations are really amenable to reordering and doing whatever you want with because they're nice separable pieces, whereas the human written stuff is just a big jumbled mess. So the potential is there, but I'm not sure we have the ideas yet. Okay, we'll take one more. The question is, for other languages, So for example, I mentioned a little bit that JS FunFuzz is a fuzzer that found a huge number of vulnerabilities in SpiderMonkey. Many languages now have a fuzzer. When I started doing this, I got a lot of hostility actually. It was very fun because I thrive on hostility. But people have come around. I don't think anybody can. I think you have to build a fuzzer if you build a new compiler, build a new language. I think you just have to do it if you want it to be very good. Eventually, I mean, not at first, right? But after a couple of years, you do. Can my tool be adapted to other languages? No. No, it's very specific. That's another dream. The generic fuzzer is a different dream, but that would be great, but no. Okay, thank you very much, everyone.